Hello, Rham. The last time we stopped by giving the statement of the decomposition theorem, but I said the last time that with this decomposition, in some cases, we can get a final decomposition, and this is in by considering a terminally ramified extension, we can decompose our differential module more. Then last time at the example, I changed the example because with degree 3 is more complicated. We can see more complicated to express how we the decomposition. Then, if we consider the differential fields of a formal long power series, and we consider this derivative, we saw the last time that the reduction of this derivative is the derivative 0, which means that we can use Hansel lemma for this derivation. Then the point that we know about this field is that any finite extension is terminally ramified, and moreover, it has this form. If it is of degree 2, then any extension, if L is an extension of K, and probably L will be finite extension, and probably L will be something like or some n. I mean, in this situation, we know that the residue characteristic of this field is equal to 0, that we don't have any problem with the m. Then the commutative polynomial associated to this one is we can decompose it easily like that. And even if these two roots have the same absolute value, by multiplying by t, the decomposition of this differential of this commutative polynomial we can decompose into two distinct parts that are co-prime. That's why we need to specify just some technique point. That's why we can lift this decomposition for the differential polynomial and got that at the and got a final decomposition. Then the point is that if we want the point, if when we multiply here, we cannot do, for example, like in the commutative case, cannot do that. We cannot do this. For example, we have this, and we just need to do this is for the commutative polynomial. However, for the non-commutative one, then in order to express this in terms of this derivation, we need to perform some for example, some transformation, and and some calculus to obtain this. Hopefully, it doesn't change. Hopefully, when we reduce to the residual fields, we will obtain the same polynomial. This part will disappear, and that's why we can lift our differential polynomial. As we can lift, then we can lift for this polynomial, and we know that this polynomial is that one. All we have to do is to multiply by this, but we need to got at the end something, two differential polynomial that are harmonic differential polynomial. That's why we will just this one, it's just and we know that it is not commutative, but we just put we commute with them, and in that case this will change and will be something like that, and this term go to this part, and then we obtain our decomposition here. The point that and this is an example, and here in some sense it is obvious that it's here the derivative extend naturally, and we can see it, and this doesn't change the norm of this derivation. How this result can be generalized for any time ramified finite extension. Now, if we consider, if we have a complete extension of K, and we consider a finite extension termly ramified, then if we have a bounded derivation, then we can extend it uniquely, and the norm are equal. However, for example, if we don't have the condition that the extension is termly ramified, this doesn't mean maybe we can, even if we can extend this derivative uniquely, the norm of the two will not remain the same, and we can see it maybe later for the Frobenius. And some fact about that, if you consider finite termly ramified extension, then if my differential field, the summinorm of the connection of the spectral summinorm of the connection is strictly greater than the norm of the derivative, then by extending the scalar to omega prime, this will not change the spectral summinorm. And this is because of this fact. Here we just use the fact of tensor product, and and we know that here, for example, endowed with this one can be seen as a differential module over omega d. That's why we have this result. And since we have this, and in that case, we know that this one, yes, this one is strictly less than this one, and we know that this one is strictly greater, then we should have the equality here, because this one is strictly greater than this one. Then we should have the equality. We already saw before that if spectral seminorm are not equal, then we should have equality in that case. Then now we will, in the literature, this definition maybe you can find it in a different way, but I prefer here to just give the example when we can show why we have this kind of equivalence. What doesn't mean this kind of equivalence? Then if we have two differential modules and we have their differential polynomial, and we consider the roots of the commutative polynomial associated to this differential polynomial, then we will just talk about this property when all the radii are small. And then we say that this then first of all that a differential module is refined if and only if we have this value. And for example, in our previous example, even if this polynomial, we can say that it is not, it is irreducible as a differential polynomial. Even if it is irreducible, then we are not in this situation. The thing is not refined. Doesn't satisfy this. Then we say it is refined if and only if we have this, which means that which means that if we reduce to the differential fields, we will have something like that. Something like that. This is what doesn't mean. And the two differential modules are equivalent if we have this the same. The point is, this is not an equivalence relation. We just need to define this relation in the refined differential module, and in the set of refined differential module, it is an equivalence relation. Then now, the good point is that if we perform, if my differential module is not refined, we can always find termly ramified extensions for which we can decompose my differential module into refined parts. And because of that, by doing a finite termly ramified extension, then we can decompose my differential module ME. So, such that each part of this decomposition. Then here we will not refine the decomposition for the part that has a spectral seminorm less or equal to the norm of the derivation. We will just do it for the part that we know that the roots are the greater, the absolute value of the root are greater than the. And that's why we can use the equivalence here. such that this means just that there is no roots that they are too close to this part. The root of this one, they are not close to the root of this one. We will separate them as follow. Then we can, the problem is if the root don't have the same absolute value, we can separate them easily. However, no, that's why we will just focus on the case if the differential module is pure, which means that it is only one part, the direct sum of the part which has a spectral. This means that we only have this, which means that the spectral norm of nabla is equal to S, and all the subquotient of M have spectral norm equal to S. And we know that we can use differential polynomial, and in this case we should have something like that because we assume that our differential module is pure. Then the point, then you can do it as an exercise, this part. And just I need to give after that maybe an equivalence why we can use that. Then we can find a termly ramified extension such that we can decompose our commutative polynomial, not our differential polynomial. But since the roots are greater than d, then it can extend in some sense to. The point is that if we reduce to by multiplying as in the previous example, when we reduce to the residue field, then we will obtain the same thing. That's why it can lift in some sense in the same way. Then we can decompose, and we will do it by induction as follow. And for example, we consider P1 is something. I just have the roots that I have at least another root for which we can separate. Then I will do the same just to obtain the same result as I did for the previous example. And this will disappear when we reduce. Why I should do that? Because here the derivative is not necessarily equal to zero. It may have a norm greater than 1. That's why, in some sense, I normalize this norm, or I make it. I make the norm of the derivation less than 1 to obtain a zero derivation. And that's why this, when we will reduce to the residual field, this will disappear. And in that case, we will obtain a part that that satisfies this. And the other part, it is exactly equal to 1. Then I can decompose in the residue field. If it is exactly equal to 1, this just means that when we reduce this element and 1, they are different. That means that we can cut our polynomial into 2, and after that I can do that for and this is not necessary. We can do that as in here. It's not. It's a multiplication. As in the previous example, we can perform and obtain something like that. Then how we can decompose it? We can do something like that. This one. not necessary. So we just explain in which part I will do that. Then just set. And for this one, I associate this differential module. For this one, I associate this differential module. For this one, I will associate this differential module. And we will get and we do the same thing as we did before. To obtain the, we use the same suffice just to take the sum of these two, and we got something like that. And they are satisfying all the, and no, and we will do that for, we will do the same by induction. We do this differential module, this one is our find. Then we will do the same for this one. And so on. And we obtain our results. Then from this theorem, I will not prove it, unfortunately, because we don't have much time. And I hope that I can give you the decomposition of the decomposition, the complete decomposition, which means with the respect of with respect to all duality. And just as a fact of this one, but there is much to prove. It's not a direct fact. There is other thing that we need to prove to obtain this this part. But this theorem helped a lot. Let's go to. And here D is equal. Such that then as a differential module, and this decompose is isomorphic to the direct sum, something like this mean in some sense that all, when if I consider the if I consider in some sense the reducible differential module are of rank 1. In that case, we can find for any reducible differential polynomial, we can find a termly ramified extension for which it became a product of differential module of differential polynomial of rank 1. This is not the case for the case when the residual field is equal to the residual characteristic is equal to P. Just to remark, if all the Fe are in K, then not even that. singularity. And in the other case, we say that the differential module is irregular. Now the case the residue characteristic is equal to some p. Then here for all, we will ask, here I didn't, here just K is supposed to be algebraically close. I say it before, but just to recall. And so is here. Sure. Here we consider we cannot choose any differential field in that case. We need to specify the kind of field that we are working with. Consider then here omega is something like that. And here for the simplicity, we will choose this derivation because it will behave nicely. It can extend, it can, it has a pullback and it has a push forward, which is nice for the Frobenius. By translation, we can even the result extend to the case when here there is no zero. It's a point AR, for example. But we will focus in that case because it can translate easily to the other case. Then I already defined the spectral radii of the differential module, then it's okay for that. Then what we need to do now, just to explain what is the push forward and what is the it's not a great notation here. We just put something like that to simplify the notation. Maybe it's better to make FR. No, over here. Just simplify the notation and we will see why after. Then from here, if we consider these fields, then I have an injection from here to here. And just by associating to t power And for this, we have is a finite extension of degree p, which is absolutely not which is totally ramified and not moderate. It's not a tamely ramified extension. It's not at all, because the degree in that case is equal to p, and if it is a point of type 2, then the extension is not separable, and if it is of type 3, then we will have the, then in that case, even in that case, it's not separable, the extension, and that's why it's not a tamely ramified extension. The point is that here, if I have the derivative d, then here, this derivative extends only this one. Why? Because maybe it can be something not understandable. Just maybe it's better to write this one and say that this is the p here, for just to not confuse between the two. Then the good point, and I told you before, if the extension is not tamely ramified, we will not have the same norm. Here we have is equal to 1 over this one. Even if this one extends this one, we have this one equal to p, because it is the same, but it's just multiplied by p. And this is, we say that it is the Frobenius up. Then if we have that differential fields. It's not only for a field. Then